Hello friends, here in this video we will see a problem based on shear force and bending moment diagram for cantilever beams. Here is the problem. Now in the question it is given, draw SFD and BMD for a cantilever beam as shown in figure. This is the diagram provided to us. Cantilever beam is fixed at one end, then it is free at the other end. It is loaded as shown in figure. Loaded at point B, C, D and E, and the values of loads are given. For such a beam we have to draw the shear force and bending moment diagram. Let us try to get the solution to this problem. Now in the solution to this problem, we are going to solve this in three simple steps. That is, I have divided this problem into three easy steps. The first one is step number 1. Calculation of support reactions. So while calculating the support reaction, if we see here, one end of the beam is fixed, so when the load is acting, and as we can see here, all the loads they are acting in the downward direction, so it means at the support A there will be a vertical reaction, and this vertical reaction will be called as reaction at A, and this reaction at A is what we have to calculate. So I'll use the condition of equilibrium, that is summation of Fy is equal to 0, where upward forces are positive and downward forces are negative. Therefore, Ra is acting upward, remaining all forces are downward. So I'll write down Ra is positive, minus 400, minus 300, minus 800 and minus 500 is equal to 0. So therefore, on calculating this, Ra value will come out to be 2000 Newton. Next, after getting this, since the beam is fixed, and in case of fixed beam there are three types of reaction. First is the vertical reaction as we see here, then there is horizontal reaction which will be called as HA. Now in this case here there are no horizontal forces acting on the beam, so this horizontal reaction will be 0. At the same time there will be moment acting, and I am assuming that moment to be acting in clockwise direction. This is my assumption that the moment is acting in the clockwise direction, called as moment at point A. So it means whenever there is fixed support, the beam cannot move in horizontal direction, it cannot move at the fixed end in the vertical direction, and it cannot rotate also. So there is a reaction which is called as the moment reaction at point A. So as first I have calculated Ra, now I will calculate the value of moment. HA value will be directly 0 because there are no horizontal forces acting on this beam. So HA will be equal to 0. Now to calculate this moment, I will say that taking moments of all forces about point A, and that will be called as summation of moment about point A. Here the convention is clockwise moment will be treated positive, anti-clockwise can be treated negative. That is the convention which I am using here. So if we see in this diagram, I want to calculate the moment at point A. 500 into 2, that is force into the distance, that is the definition of the moment, that it is force multiplied by the perpendicular distance. So force, if I take it as 500 Newton, its perpendicular distance from point A is 2 meters, So that will be plus 500 into 2, then 800 into, now the distance of point D with respect to A, here it is 0.5 and it is 0.5 from here. So from 2, if I subtract 0.5, that will give me the distance from point A, that is 1.5 meter, because this distance is 1 meter. So it will be 800 into 1.5. Next, 300 into 0.5 plus 0.5, that is 1. Next, 400 into 0.5. So therefore, on calculating, I will get the summation of moment about point A as 2700. Unit will be, the unit of force is Newton and distances are in meter, so value of bending moment will be Newton meter. That will be the unit of moment. So here we complete the step number 1, that is we have calculated the value of vertical reaction at A and the value of moment at point A. Now I will go on to step number 2. Step number 2 is called as shear force, also called as SF calculations. Now, as I have told in the start that this problem of SFD and BMD will get solved in 3 simple steps. First one was calculation of support reactions, second is shear force calculation, and for this step I will need the sign convention, so I am writing the sign convention here. Now, any shear force value to the left of the section acting in upward direction and force acting to the right and in downward direction, both of them will be treated positive. Then any shear force value acting to the left and downward direction, acting on the right and upward direction, will be treated as negative. So with the help of this sign convention, we are going to find the shear force calculation. And here I am writing a note that for cantilever beams, start calculating shear force from free end. So here I have given a small note that for cantilever beams we have to start calculating the shear force from the free end. So now here, as I have mentioned, that we are going to start for cantilever beams, start calculating shear force from free end. Now why I am doing this, starting the calculation from the free end, is this shear force will continuously go on increasing from right to left, that is from free end to fixed end. Shear force value will go on increasing. So that will help us while plotting the shear force diagram. Even if we take the shear force from the right end, that is the fixed, from the left end, that is fixed end, then also we are correct. But preferably we should take it from free end, because the shear force value will go on increasing. So first I will find shear force at point E. So SF, that is shear force at point E, is equal to, onto the beam diagram. Now I will take the section to the left of E. This is my section. If I am taking the section to the right of E, then On the right hand side of E there are no forces. It means shear force will start from 0, from point E, and then it will go on increasing. Let us check this. If I am taking the section to the left of E, then on the right hand side of E there is a downward load having value 500. So as per the convention, if a force is to the right of the section acting downward, it should be treated positive. The value is 500. Next, this shear force value will be constant from E to D, that is up to the right hand side of D. Next, if I take the section to the left of D, then the shear force will change. That is, here is our section, and on the right hand side of this section there are two forces, 800 and 500. Both are acting downward. So on the right hand side, downward is treated positive. So that will be SF at point D plus 500 plus 800, which gives me plus 1300 Newton. Next, this value of shear force will carry on from D to C, that is, it will continue up to the right hand side of C. Next, if I am taking the section to the left hand side of C, then on right hand side I have three forces, 300, 800, 500, all are acting downward. So on the right hand side, downward is treated as positive, so that will be SF at point C is equal to plus 500 plus 800 plus 300, that gives me plus 1600 Newton. Now this value of shear force will go on to be constant up to the right hand side of B, that is, the value will be 1600 Newton. Next, if I take the section to the left of B, then I even have this 400 Newton force, so that will be addition of all forces. Which gives me plus 2000 Newton. Now this force, this shear force value will remain constant from B to A, and if I see here, reaction at A was also 2000, so the value will remain constant of shear force between B to A, it will remain 2000 Newton. So here we have found out the shear force value at point B, and then at last SF, shear force at point A, will also be same, plus 2000 Newton. That is, by taking the section up to the right of A, then to the left of the section we have 2000 acting upward. So to the left of section, upward force is positive, plus 2000. If I take the section here, that is on the left hand side of A, so on this side, that is to the left of A, there are no forces, means shear force will finally be 0. So here I am going to plot the shear force diagram, and for that I have to draw the beam again. So I am drawing that cantilever which is given in the problem. Now, for this cantilever beam, I am drawing the shear force diagram. First, I will plot a horizontal line. This horizontal line indicates zero shear force, that is 0 kilonewton value. If I see step number second, which we had solved here, shear force at point E, it is having plus 500 Newton. So at E, I'll plot the value plus 500 Newton. Now this 500 Newton will go up to point D, or we can say to the right of D. So between E to D, as there are no forces, the shear force value will be constant. It will remain 500 Newton. Next, at point D, the value goes up to plus 1300 Newton. So it will increase. It will be 1300 Newton plus. This value will go up to the right of C, as between D to C there are no forces. So here it is 1300 Newton. So now, as we are plotting the shear force diagram, at point C the load is 1300 Newton. Next, the moment load acts at point C, the value goes up to 1600 Newton, means the value to the right of C is 1300 Newton. To the left of C, it will become 1600 Newton. Then this value of 1600 Newton will continue from C to B, as there is no load from C to B. So here the value of shear force is 1600 Newton to the right of B. Next, to the left of B, it is 2000 Newton. So at point B, the value increases up to 2000 Newton. Now this value of shear force will be constant from B to A, as there is no load from B to A. Newton, and finally the value will be 0 here if I take the section to the left of A where there are no forces. So this is the complete shear force diagram, and as we see here, all the values are positive, so I'll write a positive sign here, which indicates the shear force diagram is positive throughout. Here I make this small section. So this completes our step number 2. Now step number 3. In step 3 we have bending moment, that is BM calculations. Now for the bending moment calculations, again we need to have the sign convention. To the left of section, clockwise moment, and to the right of section, anti-clockwise moment. Both are treated as positive. Then to the left, anti-clockwise moment, and to the right, clockwise moment. Both are treated as negative. And here I'll write another note. So here, as I have written, for cantilever beams, bending moment at free end is equal to 0, because when the load will be acting at the free end, this point E will bend. So if it is bending, there is no reaction bending moment at point E. So that is why the moment at E is equal to 0. Now I will calculate the moment at point D. So first I will write down moment at for free end, moment at E is equal to 0, since it is free end. Then moment at point D is equal to, see, if we look at point D is dividing the beam into two parts, that is portion DE and portion ABCD. So if I see here, to the right of D, there is only one force, so bending moment calculation becomes simple. So I'll use this force, that is 500. Even if I calculate from the left hand side, then also it is correct, but for the simplicity purpose, here I am taking only the right hand section, because even if I take the left hand section, I will get the same answer. So here the moment at D will be equal to 500 into 0.5, and this moment will be in clockwise direction. So point D is here, force is on the right hand side of D, so moment is produced clockwise to the right. So here, by the sign convention, clockwise moment on right hand side is negative, so that will be minus 500 into 0.5, which is minus 250, and the unit is force into distance, because that is moment. So force is Newton, distance is meter, so unit is Newton into meter. Next, moment at point C is equal to, again here we have point C, so on the right hand side 500 into 1 producing clockwise, so negative. Then 800 into this distance from C to D is 0.5 meter. So 800 into 0.5, again clockwise, so minus 800 into 0.5. Since on the right hand side of the section, clockwise moment is negative. So this gives me the value as minus 900 Newton meter. Moment at point B will be equal to now, if I see point B, on the right hand side of B there are 1, 2 and 3, there are 3 forces. On the left hand side I have RA, so this will be producing a moment in clockwise direction. So to the left of B, clockwise moment is treated as positive, so here RA into 0.5. So now here I will be calculating the moment at point B, that will be 500 into 2, here this is 1.5, so 500 into 1.5, and since it is clockwise to the right, so negative, minus 500 into 1.5, then minus 800 into 1, next minus 300 into 0.5. So from this I will get the moment at point B is equal to, it is minus 1700 Newton meter. Moment at B. Next, moment at point A is equal to minus 500 into 2 minus 800 into 1.5. Next, minus 300 into 1 minus 400 into 0.5. So this gives me the value as minus 2700 Newton meter. So these are the values of bending moment, and now we can plot them onto the bending moment diagram. This is zero line, 0 kilonewton meter. Next, if we start the bending moment here, bending moment at point E it was 0, so at E it is 0 value. At D the value is minus 250, so minus 250 means it will be below this line. Newton meter. Actually these loads, these moments, they are in form of Newton, so that will be 0 kilonewton meter, Newton meter. So this is not in terms of kilonewton, actually it is Newton. Then it is minus 900, so again downward. Next, at B it is minus 1700. At A it is minus 2700 Newton meter. So now I have to join all these bending moments. So whenever there is no load between 2 points, that is from E to D, there is no load. Shear force was a straight line, bending moment will be an inclined line. Then again there is no load from D to C, shear force was straight line, bending moment should be an inclined line. Similarly from C to B there is no load, so bending moment will be an inclined line. Next, from B to A there is no load, again there is an inclined line for bending moment. And finally this value will be 0. And here we have the negative sign. So this is the BMD, that is bending moment diagram. So here we have completed the SFD and BMD. BMD, the third step was completed, and with this we complete the question.